All right, so we are here more than halfway through the semester. And we're down to chapter 9 here, graphs and algorithms. And I'm just going to talk about that. I don't have a new project for you. We already have enough projects that are required for the whole semester. I'd still like to do a few more. In particular, there's one I'd like to add where you have to find paths, all the paths, and you have to keep backtracing. I haven't quite figured out how to do it yet, but it's quite appropriate for the tree traversal techniques we've been talking about. There's a challenge that's like that. Anyway, let's start with chapter 9 here. So, in theoretical mathematics, and therefore computer science, there is this thing called a graph, which is it's not exactly a data structure, it's just a geometrical structure, but it's the kind of thing that many problems can be represented by. And so a graph is just a series of vertices connected by edges. So you can travel from A to B, you can travel from B to E. Here, D goes in a circle. You can take this path from D and come back to D. So that's kind of screwy. But anyway, you can represent this in various ways. V, here's the vertices, A, B, C, D, E. And here's the edges. A can go to B, A can go to C, B can go to C, and so on. So this is one way to do it. You could have a set of vertices and then a set of sets showing the connecting points. And of course, we're going to talk more about the best way to represent this in computers and use it. But this is the general problem that applies to maps and many other things, like industrial processes and so on. So a node or vertex is the endpoint. Edges are the things that connect two vertices. A loop is when you go from a nudge and just come right back to yourself. And there's a thing called the degree, which is the number of edges coming in. So this thing C has a degree of 3 because it connects to 3 other vertices. A has a degree of 2, and the degree of B is 4. So adjacency is two things are adjacent if there is a path to go from one to the other that doesn't pass through another node, a direct trip. And the path is a series of vertices and edges between two nodes. So if you want to get from C to E, you could go from C to E, you could go CABE, that's one path. And CBE would be another path, and CDE would be another. And you could do CDBE. And I've certainly been looking at this for many years because of the internet. The whole point of the internet is like this. It's an overly connected graph. There are more of these connections than you need. So if one of these wires broke, like this one, you could still get places. And then if another one broke like this one, you could still get places, and that's the thing of the internet. A lot of the parts of the internet could go down, but the rest of it would keep working until you actually break so much of it that there are regions that cannot get to other regions. And a leaf has degree 1. There are no examples of a leaf in this graph, but you could have a leaf if there was something just connected to one of these. And that's, by the way, what home networks are. Home networks are a leaf node, effectively, because you don't have many computers at your home connected to each other. Typically, you just have one, and it goes to the internet. So anyway, so here's some types of graphs. A directed graph is where the edges are not just an undirected graph is the kind we've had before, just simple lines like roads. Roads, I guess, can carry traffic both ways. All it tells you is they are connected. But a directed graph has arrows on them, so this is one-way roads. You can go from A to B, but you can't go from B to A. And so you have this, by the way, is a loop. There's nothing forbidding loops in a directed graph. The only thing directed tells you is that the links, the edges, have directions. And you can now count the in degree and the out degree. Before we would have said here that every node here has degree 2. There are 2 paths coming into each node. Here, we could say, like B has an in degree of 1, an in degree of 2, and an out degree of 1. You count how many nodes are coming in and how many nodes are going out. So that's an issue. And therefore, that's the in degree and the out degree. So if you look at E, E has an in degree of 1 and an out degree of 2. There's 1 feeding in and 2 ways to go out. All right. And so, if you think about these like water pipes carrying water, the water is flowing this way, it flows to here, and then there's 2 places it can go, that sort of thing. So an isolated vertex like G has degree 0, no way in or no way out. A source vertex like A only has out degrees but no in degrees, so if this was water, the water can flow out, but there's no way to fill it. And a sink vertex is like F, where things can flow in, but they never go out. So this is a place like a drain, where you just throw stuff in and it throws as much as you want in and just keeps going away. All right. So then there's a directed acyclic graph, which means it's directed, so there are arrows on the edges, and it's acyclic. There is no loop. If you go to C, you can't go around this loop. You can't go around this loop. If you go to B, there's no way to get out of B, so there's no way to make a loop. When I first looked at this, I thought there was a loop, A, B, D, A, but there isn't because B is going the wrong way. So this is acyclic. That's very important in networking. We're going to get to spanning trees soon. You cannot allow any cycles in an Ethernet network, or most networks, because packets would get lost going around and around and around the cycle. Let me check the Twitch for comments. No new ones? All right, good. All right, so you have a weighted graph, which is typically what you have. In addition to having a direction, you also have a weight, which measures something important about that, like the distance or the cost or the fuel consumed or anything. Could be all different things, but some kind of, it turns out to be important not just to know what is connected to what, but something else. In computer networks, what you usually rate them by is the speed of the network. So here, if you want to get to D, you could take the straight hop, but that would have a certain speed, or maybe you want to go through these other devices, and if these are faster, you might be better off taking the path with more hops that might get you there faster than this slow link, that sort of thing. All right, then bipartite graph is what happens if you have nodes in two different categories. So you have, for example, applicants and jobs. And so each applicant might be qualified for certain jobs, and you could represent that here, but there is no meaning for an applicant being connected to another applicant or a job being connected to another job. You'll have links across from between the sets, but no links within the sets. So that's bipartite. And then there are ways to represent it, and how we're going to store these in memory to get things done. And there's two basic ways. You can do it with a list, or you can do it with a matrix. So for a sparse graph with only a few edges, the list is better. For a complicated graph, then a matrix is better. So here's the list. You have A, B, C, D, E, and F. And so you define a list for each vertex. The vertex A is connected to B and C. The vertex B is connected to A, C, and E. F is connected only to C, and so on. So now you have a separate list for each vertex, and therefore the vertex labels don't appear directly in the list. The source vertex doesn't appear, so it's a little clumsy to use this kind of structure. What would be better would be to store it instead of lists as a dictionary. Now you can have the vertices be the index in a dictionary, and the data stored be the list, and this is a handy way to do it. Now it's easy to refer to the nodes and answer a question. Now, however, if you want to know if there's a node connecting C and F, you could go to C and see if F is in that list, or you could go to F and see if C is in that list. So I don't think that's so difficult, but anyway, they regard it as difficult in your book. There must be an easier ways coming up. That's not too much work, but it would be even easier if you did it this way. If you just had one edge here and one edge here, and you just fill in this matrix with how strong the connection is. If it's an unweighted graph, then it's just a 0 or 1, true or false. If it's weighted, then you put the weight in here, and now you just look up in this matrix to see if C is connected to F. You see it is. There's a 1 here. So that's another way to do it. And so there's the code for it, which is pretty simple. This is going to make the matrix, which you're going to make as a list of lists, which is what you have. There are no two-dimensional arrays in Python. What you do is you make a list of lists, which amounts to the same thing. And then you have what's in here are tuples connecting the edges, A to B, A to C, B to E, and so on. That's one way to store it. And to make an adjacency matrix, you go down here, and for each edge, you put them in here. This is where you make this list. So if you frequently need to look up the presences all over the place and you want sort of random access to it, then this is a fast way to do it. Now, if you're frequently adding or deleting nodes, that would be expensive, because adding or deleting a node requires restructuring the whole matrix to have a different size. And that's annoying. In that case, just a list of the connections would be easier to maintain. Check for comments. There are no new comments. All right. So now we talk about traversing a graph. So you have a graph, and you would like to visit every vertex. And you're going to keep track and not waste your time going around loops or visiting the same one more than once. So it's like tree traversal. It's basically a generalization of tree traversal. So the breadth first search is one way. Start at the root node, then all the nodes connected to it, then all the nodes 2 hops from it, and so on. So if you have a graph like this and you're starting at A, then first you take everyone and get to 1 hop from A, which is going to be E, C, and B. You put them in the queue for later visiting, and they put them in alphabetical order for no particular reason, but that's one way to do it. So we currently have visited A, and these are the ones we're going to visit in a queue. Then we move the next one from the queue and visit it, so we're going to visit B. So that leaves C and E waiting in the queue, and B, you see if there are any new nodes you can reach from there, and you can reach D as the only new node, so you add that to the list, to queue. So next we're going to visit C, because it's in the queue. And when we visit C, we're going to see that the only new thing we could reach is D, but that's not new. We already reached it from B, so we do not add anything to the queue. And now we'll just visit E and D as they list on the queue, and that'll do it. So that gets us visiting everything without wasting time with these simple 2 lists here, a queue and just a list of ones we visited. So that's the breadth first search. And so here's how it looks. Now we're going to do another example with a more complicated graph, which you can see is a little more of a mess. And we're going to again start at A. So when you, there's the code that does it. We'll just talk about it. So when you visit A can go directly to D, G, and B. So you add them in alphabetical order to the queue. The next thing you do is visit B, because it's in the queue. And when you do, B can reach E, but E was already in the queue. It could also reach F, so we add F to the queue. The next one to visit is D, that's in the queue. When we go down there, we're not going to have anything new because it can go to F and A, but we already have F in the queue. So we visit D, and the same thing's true of G and E. You can visit them because they're in the queue, but they don't open up any new paths to get anywhere new. So we've reached everything that we can reach 1 hop from A, and even this thing, which is 2 hops from A. So now we go we visit F. Because F was here, D made a pass to F and we added it to the queue, so we visit F, and when we visit F, we can now reach C, which has not been visited yet, so that puts C in the queue, visit C, and now you can visit H. So that's the order in which you visit all the nodes. It's just another way to find every node and visit them all and make sure you don't waste any time. So that's breadth first, and so the time complexity is the order of the number of vertexes plus the number of edges. All right, linear in that. So this can be used to find the shortest path, a web crawler, navigation system, things like that, where you're trying to hop through. And hyperlinks, by the way, are like this. You have a page, it has links, you jump on those links, they go to other pages, they have more links. Some of those links go back to where you've been, some of them go someplace new. So trying to build a spider like Google's, to spider the web, to find all the pages out there, to index them, you need a web crawler. And it's the same problem. You have this complicated structure of nodes connected to other nodes, and you're trying to efficiently index it. So depth first search is the alternative. You do not hop one in every direction. You hop in one direction and keep hopping down, down, down until you hit the end. So visit a new adjacent node until you get a dead end, then backtrack and find alternative paths. And you'll end when the backtracking hits the root node and there's nothing new to go to from the root. So here the root here is A. So the first thing we do is go to B, and B is the end. We can't go anywhere from there. So we'll backtrack back to A and try the other child of A. So that's what you start here. First you go to A, and you see that you can now first you put A, you're visited, and you see there's a node called B, so you put it on the queue. Then you elevate B to the visited list, and B does not open up anything new. So you have to backtrack and see that there's S you haven't visited yet, so you add that to the queue. That's the idea. So you visit the other neighbor S, that opens up C and G, so you just visit the first one you have not visited before in alphabetical order, which is C. You put it on the stack. I guess they're using a stack instead of a queue. Anyway, so then you so now you visit C, and these three are possibilities. So you take the lowest alphabetic one, which is D, and put it on the top of the stack. Then you visit D, but D doesn't lead anywhere new. So you now backtrack up to C, and C has E and F, so you add E to the stack, then you visit E, and E can go to H, and you always go down if you can, so you put H on the queue, which is a stack, I should say, this time, and then you've been to H, and now H has a neighbor, G. So you visit G, because you always want to go down as far as possible. Now here, we haven't exactly hit a dead end yet, because there's a new place we can get to called F. So we've taken this long path to get to F, because we've gone as deep as possible before we execute breadth. So you could argue this is kind of wasteful. If we'd done a breadth first search, we would have hit F a lot earlier. But anyway, that's the way it works. We put F on there, and now we visited everything. That's the depth first search. You go as deep as possible, and then you check what you skipped by backtracking. So this complexity is the order of V plus E if you use an adjacency list, and V squared if you use an adjacency matrix. So you can just see when one would be better than another. So this is used to find connected components, cycle detection, solving maze problems, finding bridges, where one essential link that would disconnect the graph. You call these, in networking, you call these single points of failure, where one link would fail and that would cause you to lose connectivity. So minimum spanning tree is the application of this I most see. If you learn to do network forensics, you examine the network traffic on any modern computer network, you will find tons of STP packets, spanning tree protocol. This is necessary. Every network is constantly checking to make sure there are no loops. And so if you have a network connected like this, there are many loops. You can make a loop HCH, you can go ABF, you can go ABEF. There are many cycles here, and cycles are bad in computer networks. So you would like to get to a spanning tree that connects every node to other nodes without any loops. So you don't have packets that are just running around in loops, getting nowhere. So there are two algorithms. This is a greedy algorithm called Kruskal's algorithm, and it goes like this. Go for the whole tree, find the lowest cost edge, and add it in. Then do that again, every time check to make sure you haven't created a cycle. Just keep adding the lowest cost edges and not forming a cycle until you connected everything. So start with an empty minimum spanning tree list, sort the edges according to weight, add the lowest one to the next lowest, making sure you don't add a cycle. So that's the game. So here we have a graph with loops and weights. So here's the lowest one is 1, so you add that to your minimum spanning tree. The next lowest one is 2, and it doesn't create a loop, so you add that one. The next one is 3, and even though it's disconnected from the others, you don't care in Kruskal's algorithm, you just add 3, and it doesn't create a loop. That's all that matters. Now, you add 4 and 5. Here's 5, and here's 4. So those do not create loops, and now finally the thing is connected. 1, 2, 5, 3, 4. So you've got sort of open C shape here, but you haven't connected all the nodes yet. So now add line 6, which is here, and that doesn't create a loop because you haven't added line 9 yet. But now that you've done that, if you add 7, that's going to create a loop here. If you add 8, that's going to create a loop here, a big loop. If you add 9, that's going to create a loop up here, this little triangle, so you don't add any of them. And you add 10, which gets you to the last point. Now you've connected all the vertices, so you're done. That's the final spanning tree, where there is a path from each node to each other without having any loops. And this is what happens automatically in computer networks. It sends signals to detect these, and it automatically turns off some of the links to prevent loops. All right, now, so there's a lot of issues here. Like I mentioned, computer networks are a good one. Anything else where you're trying to find paths to visit anything like a map without having loops, electric grids, that sort of thing. And so the time complexity is E log E or E log V, because you have to consider each edge, and you also have to consider the vertices, but the vertices might be, there might be sort of tree structure where you don't really have to consider them all. You're viewing paths through it. So I don't know exactly why it's log E or log V, but I can imagine it's sort of like a tree, which you talked about before. Then there's another one, prim's minimum, which is very similar, it's just a little different. Create a dictionary that holds all the edges and their weights, then get the edges that have the lowest cost and grow the tree. But here what you do is you choose the lowest cost from the vertex. You grow from one edge. So here, we start with A to C, of course. That's the shortest path from A to C. The shortest path available, we start the same as the last one. But now, we want to grow from here. So we add 2, this is the next one. Now remember last time we jumped down here and add 3. But this time, we're only going to consider edges that go from what we've already connected. So the shortest, the ones A, C, and E that are already connected have this path 9, 6, 8, 7, and 5. So the next one we're going to add is going to be 5, because we grow from the existing tree instead of making isolated regions that are connected and letting them connect later. So the shortest path from the tree was BD. This time from the tree we have, it's going to be this one, BD. And then from that tree, it's going to be DG. And same thing, you're growing just from one edge, adding the shortest edge that is connected to the stuff you've already put in your path. And when there's nothing you can do, you end up with essentially the same thing. The minimum spanning tree is just another way to get there. And of course, the only reason we have 2 algorithms is because they have different efficiencies. So in Kruskal's is E log V, prim's is E plus V log V. So if you have a dense graph with many edges, more edges than vertices, like the internet, where there are many ways to go from each direction, then prim's is better, because E is big, and you'd rather have order of E than order of E log V. For a sparse graph, Kruskal's is better. If the E is equal to V, which is what a sparse graph would be, then this is V log V, and this is V log V plus something more, so Kruskal's would be better. That's all. All right, let me check for comments. Nothing new. All right, let's try a Kahoot, which is chapter 9 here. All right. People still coming in. All right. All right. So what's the degree of a vertex? That's the number of edges coming into it. That's the degree. All right. Which vertex has out degree 0? The sink. There is no way to get out. Things can come in, but nothing can go out. That's out degree 0. That's a sink. All right. Now, I suppose an isolated one also has out degree 0. but it also has in degree zero. Perhaps I could improve that question, but anyway, sync is the one that I think is the best answer, although one could argue. Part of why these things are extra credit. They're not always terribly fair. Anyway, all right. All right, so which structure is appropriate for matching customers with purchases? One-to-many relationship that you think of when you do database administration, which I've spent a lot of my career doing. That's a bipartite graph. One customer can have many purchases, but if the customer doesn't connect to a customer, and the purchases don't connect to purchases. So that's bipartite. All right. All right. What structure will connect all the nodes of a graph without a cycle? It's a DAG, directly acyclic graph. All right, good. All right, good. Stop this recording.